Hi there, my name is Ben Rodney with ASHRAE New York, and on behalf of the ASHRAE New York Board of Governors, I want to welcome you to this recording of our guest speaker at this monthly chapter meeting. We're excited to continue to bring content to our members and guests and hope that you'll follow our new YouTube channel by hitting the subscribe button just below this video and then hitting the bell to get notifications on any content posted to the channel. You can also follow us on LinkedIn, Instagram, and go to our website, ashraeny.org, where you can sign up for our newsletter, check our events calendar, and hopefully join us as a new member of the chapter. If you have any questions, comments, or conversation about this video, just leave them in the comments section below. Thank you, and enjoy the presentation.
Thank you for joining us for our May webinar meeting. I'd like to take a few minutes to talk about sponsorship and research promotion. Sponsorship is vital to ASHRAE New York's operation and funds all of our chapter events, our student scholarships, and research promotion. ASHRAE Research Promotion is a program that was established about 100 years ago to fund research to advance HVAC technologies. Today, ASHRAE funds over $2 million in advancing HVAC research and updating our standards and handbooks. And that includes research on improving interior air quality, which we all know is of primary concern today. In fact, ASHRAE has set up an epidemic task force on March 31st to address current and future pandemic challenges that affect the HVAC industry. Now, where does this funding come from? Research funding primarily comes from its members through individual member donations and company sponsorships. This is raised at the chapter level, and each chapter is assigned an annual goal by ASHRAE National. We have been fairly successful in raising about a little over 75% of our target, and we have until end of June to achieve this goal. So I'd like to take this opportunity and request anyone interested in becoming a sponsor or making an individual donation to research promotion. You can log on to ASHRAE's website, ashraenewyork.org/sponsorship for company sponsorship. And we have sponsorship packages listed over there for you to select what tier you'd like to sponsor. And if you'd like to make an individual contribution, then you can also log on to ashrae.org/rp. And if you have any questions, you can shoot an email to sponsor@ashraenewyork.org. I would like to take this opportunity now to thank our current sponsors. I'm going to start with our tier 1 leaders: Carrier, Con Edison, WSP, CDE, SRS. Our tier 2 partners: Trane, Fulcrum Group, Goldman Copeland Consulting Engineers, Tech Systems, JB&B, Mitsubishi Electric, AKF, Cisco Hennessy Group, EDE Systems, Fleet, Technical Air Systems, Belimo. Our tier 3 supporters: ADS Engineers, Chimney Design Solutions, Federal Pump, Schneider Electric, Johnson Controls, National Air Filter, Vitolic, Cerami, Wallace Ennis Associates, Siemens, Daikin, Thermal Systems Associates, EcoCare Corporation, and Skyline Engineering. Now I'd like to hand it over to Natalie to introduce tonight's speaker.
All right, thank you, Sarvesh. Just a few more announcements before I introduce Mark. A couple of upcoming events are this Thursday. We're having our 4th installment of the designer series, and that's on smart buildings, and it's going to be given by James Coleman from JB&B. We also have the 5th and 6th designer series are coming up in the next 2 weeks, as well as we are having a dinner meeting in June. Please note that we are doing a date change, so instead of Tuesday, we're doing a Thursday. And all of this information is currently up on our website if you would like to sign up. For today's event, please make sure at the end of the event you fill out the questionnaire, because that is how we are tracking attendance for PDH certificates. If you've been attending our webinars, you will know that we will send out an email with the certificate after the event. So please make sure you do close that out. If you have a pop-up blocker, or I know in my case it opens up an Internet Explorer for some reason, just be mindful. And if you don't receive a pop-up, just make sure you please tell someone from ASHRAE. Okay, so on to our speaker for tonight is Mark MacCracken. He is currently a ASHRAE Distinguished Lecturer and the VP of the Calmac Portfolio for Trane. He served on the board for the board of directors for Urban Green, New Buildings Institute, and AHRAE. Please welcome Mark.
Well, thank you very much, Natalie. Let's see, I will take over control of the screen. Tell me when you can see it. Coming through, Natalie?
Yes, it's coming through just fine. If anybody has any technical issues, just use the questions box, and also at the end for our Q&A portion, you can type your questions in there.
All right. Well, thank you very much, Natalie. I appreciate the introduction. And I'm talking today about somewhat of a new topic. I've been talking about energy storage for a long time. I've been in the industry over 42 years, and most of that has been in the energy storage world. But today I'm going to talk about electrification, heat pumps, and energy storage, and how we can reduce our carbon emissions in our buildings. Let's see, the forward button I assume should have worked here. There we go. You've read their abstract, you probably why you're here. I'm going to explain some of the learning objectives. We're going to go over electrification. You'll get a clear understanding of thermal energy, and we'll talk about absolute zero from back in high school days. We're going to show a bit how thermal energy storage systems can help in a building and free cool kind of in a different way without throwing the energy away. Talk about water and how unique and precious substance it is, and then demonstrate how heat pumps can heat very effectively in our buildings. You know, when I think most people now know of electrification, the easiest example is if we're going to, you know, get rid of carbon emissions from automobiles, you got to make them electric and supply it with a clean grid, because there's no way, you know, to be burning the fossil fuel on it and have it be a zero carbon car. It's the same thing with buildings. Easiest way to think about it is just you're going to turn off the gas pipe or whatever pipe and not bring fossil fuels into the building. And so if that's the case, if that's it going forward, now there's all sorts of debates, you know, will we be able to get such a clean grid? And I'm not going to go into all of that, but certainly if you're burning fossil fuels in a building, it's not going to be carbon free. So the first thing to think about is chillers are big heat pumps. You know, electrification means big heat pumps, or that's what it certainly does to me. And chillers are big heat pumps. The big difference is that they're not reversible, right? The evaporator is always the evaporator, the condenser is always the condensers, but it's going one direction. And big water-cooled chillers are big water-to-water heat pumps. So we hear about ground source heat pumps and air source heat pumps. And really, it's almost a misnomer to be calling these things heat pumps. They're actually energy pumps. They pump energy from one temperature level to another temperature level. And I think for people that are not on the technical side, sometimes that kind of helps. Now, most of the people in the audience probably know these tanks. They are, normally referred to as ice storage tanks. And I got a purist writing me a letter about 10 years ago and say, your tanks don't store energy, right? And he's actually right. The ice tanks don't store energy. It's really the reverse. When you take energy out, when you take the energy out, the water turns to ice. When you put energy in, you're charging it with energy, and now the ice melts. So it's the complete opposite of what we've always been saying, charge the tanks, discharge the tanks, but we were charging them with ice. But now we're talking about energy. So we're looking at these as thermal storage devices, and we're going to be storing either heat or cooling, depending on which way the energy is flowing and what you really need. We're storing energy. My father, he was in this business. He was a great inventor, 80 US patents. And he said to me once, burning a wooden match is equivalent to about 1 BTU of energy. So I thought it would help the graphic. So if you have 1 pound of water in a beaker and it's at 32 degrees, you burn 1 match underneath it. And if all the energy goes in there, that water is going to go to 33 degrees. And by definition, that's 1 BTU. So also, if you have 1 pound of ice in that beaker, it takes 144 BTUs. So 144 wooden matches, and all that energy just changes it from phase, from the solid phase to the liquid phase. So it's a phase change material. It's changing from a solid to a liquid, and it absorbs a tremendous amount of energy when it does that. Now, water, it's a pretty unique substance, right? So if we go back to our physics or science classes in high school, we all learned about absolute zero. And there's really energy, there's thermal energy in everything above absolute zero. So on the Fahrenheit scale, it changes at 32, but in the Rankine scale, which is still the same denomination as Fahrenheit, but it starts at 0. Water changes phase at 491 degrees, right? So there's a lot of energy in cold water. Now, if you look at the sensible heat of solid water, or H2O, it's about 1 BTU per pound. So from going from absolute 0 all the way up to 492, or we'll call it 32 degrees, it has about 202 BTUs of energy in it. But then it hits this phase change, and it's going to go from a solid to a liquid, and it absorbs almost the same amount of energy, staying at the same temperature when it changes phase. It goes another 144, so that's going straight up. And this phase change happens really close to where we need it for comfort cooling. Okay, so it just happens to be that way. It also goes through another phase change, obviously, from water to vapor, and that's an even bigger phase change. That's about 1,000 BTUs per pound. But those are the two major phase changes. So, these as ice storage tanks. Well, let's look at them as thermal storage tanks, right? If you look at the pounds of water associated with them, it's essentially in each one of these tanks that are 8.5 foot in diameter, 8.5 feet tall, you've got 2 million BTUs of energy, right? Now that's equivalent to 14 gallons of fuel oil, about 20 therms of natural gas, about 2,000 pounds of steam, or 160 ton hours of cooling, if you want to look at it that way. And so we have different projects in the city, and you can look at these tanks and how much value is associated with the energy in them if you consider the regular price of fuel oil or therms or steam. So it's not an insignificant amount of energy that's in these tanks. So now let's look at heating and cooling buildings with the assumption that you've got heat pumps. So before the heat pumps, we had, when you have simultaneous heating and cooling in buildings in New York, you've got usually a boiler that does the perimeter zones, and you'll have a chiller doing the central zones or the whole building if it's the summertime. But in the fall and winter and spring, we have free cooling, so economizer cycle, right? And so essentially, we call it free cooling, and we are using the cold air outside to cool the cooling tower water, evaporate it, and we cool the space. Well, if you look at this on an energy, from an energy point of view, this is throwing away energy, right? You've got too much energy in the core of the building. It gets too warm, and so we just throw that energy away to the atmosphere, okay? Well, if local law 97 is forcing us to think about heat pumps and electrification. And so obviously the first thought is, why would you reject this energy when there is simultaneous heating and cooling going on in a building? So in the dead of winter, when the core is overheating, but you still need, heat in the perimeter of the building, why aren't you just heat pumping it and running a chiller and having the heat from the condenser of the chiller go to the skin of the building? So, a very good idea. It certainly works, and we're moving in this direction as we're designing new buildings. It makes a total amount of sense. As I described, the free cooling, you're essentially intentionally throwing energy away. So as we get into electrification, energy is going to be more and more important to keep in the building. It's actually not free. You're throwing that energy away. Maybe you're using a lot of cooling tower pumps and fans in order to get rid of it. But what if it could be stored? If we had heating the next day, if it wasn't simultaneous, what if it could be stored? Well, if that tank was filled with frozen water, if you added storage tanks to the building, if the tanks were frozen, you would just use the ice to cool the space just like you do in the dead of the summer. And now your goal is to melt those tanks and have water be in those tanks. And so you have the tanks cooling the core of the building on the winter afternoons when it's overheated, and you just have this ice, and you're now storing today's waste energy. And what are you storing it for? You're storing it for tomorrow morning's warm up. So as odd as it sounds, melting ice is storing energy, and it can be a real source for a heat pump, and that heat pump is really a chiller. So I've kind of termed this a storage source heat pump. We have ground source and air source and water source. Well, the source of the energy here is going to be coming, when we're doing the heating, is going to be coming from storage. So now in the goal on a cold winter day would be somehow to capture as much waste energy as you can and have those tanks be fully water at the end of the day of your collection period of this waste energy. Now it's in a very great COP process, and I'll go into the details of that in a few minutes. It's going to be saving a lot of carbon because now you've got the energy, and now you're going to heat pump it up to a usable level. Your operating costs can go down, which I'll go into later. And the thing that I didn't really realize when I was first talking about this is water usage. I mean, when you're evaporating water in that cooling tower, you are evaporating a lot of water in order to be able to do that free cooling. So you're also using energy and water in order to be doing that free cooling. So we'll talk about that a little bit more in a minute. So one of the questions certainly comes up, is there enough energy, waste energy in these buildings on a winter day? Well, I talked to a buddy that has one of our installations in New York City. They got 44 tanks, which was that example I used before. And they have been using their storage system to free cool the building for a decade or more already. And I asked them why, and they said, well, it's cheaper actually. And I'm like, really? And they say, yeah. And so they went into the analysis of when you're running free cooling, you got a lot of cooling tower fans running, and you've got major pumps running, and all that's running on peak. Whereas when you charge up the ice tank, it's running at very high efficiencies at nighttime on a colder winter night, and it's all off-peak energy. So, they've made the case it's cheaper. So that's why they're doing it. Well, I asked, how much of the ice do you melt every day on a cold winter day? He said all of it. So, on just a first blush, there's a lot of energy in these buildings. So that's the equivalent of 88 million BTUs that he has in that water. Now, right now, they're not using the system I'm about to describe, but certainly they could. So let's kind of look at the diagrams of what the flow diagrams would look like on this. If you were heating with a storage source heat pump in the morning, well, you really just have a chiller making ice as you would in the summertime, but that energy, that condenser energy, is not going to the cooling tower, which is where you'd be throwing it out of the building. That energy is going, we'll call it here now, to a plate and frame, and that energy is going to heating the perimeter or whatever heating zones that you have. I'm showing a centrifugal chiller here with 95-degree supply water going to those coils. I'm being told that can be done now. I think it's terrific. It's an extremely efficient process. If you needed higher temperatures, you may use a screw or a scroll or something of that nature. But the point is, you've got a lot of energy in the tanks when they are full of water, and we're going to take that energy and we're going to pump it up to a usable level. In the simultaneous mode, you're going to run the chiller. You're not going to be doing anything with the tanks. And if you've got energy, if the core of the building is too warm, you are going to cool the building as you normally would, and the energy from the cooling coils is going to go to the chiller. It's going to get heat pumped up to a usable level and go into the heating coils of the building. So you can use that chiller for whenever there's a simultaneous heating and cooling mode. And if it wasn't the same balance, you could use the tanks if you needed more heat, or use the tanks if you needed less. Winter cooling mode, well, that's pretty easy. You've got storage tanks that are now devoid of energy, so they're ice, they're in the solid mode. And so now the chiller is not running. We're just going to circulate liquid through the tanks, just as you would be cooling the core in the summer, or the building, wherever it is in the building. You're going to be running the pumps and just taking the energy out of the building and putting it into the tanks and starting to charge up the tanks with energy. In the summertime, you've kind of seen the mode often. Now we are going to use the chiller. This is what would be called partial storage. If you had a 2,000-ton building and you had a 1,000-ton chiller, maybe 1,000 tons is coming from the chiller at this point, and you could get another 1,000 from the storage. So the storage is doing part of the load, hence the name partial storage. So the chiller is running, and you're rejecting some of the energy out of the cooling tower, okay? And you are absorbing some of that energy in the storage tanks to be rejected later in the summer. So on a summer night, you've got all this energy in the tanks. They're water. They got a lot of water, and now we got to get the energy out of the building or out of the tanks. And so we're going to run the chiller. Oops, I'm sorry. This was summer daytime cooling mode. This is without the chiller running. So now it's full storage. Maybe you'd be using this as a demand response situation where you want to turn the chiller off, and now the storage is meeting the load totally. So on that summer night, as I started describing, now you've got tanks that are water, mainly water, and you got to get rid of that energy out of this storage device. And so we're going to run those chillers at night. We're going to dump that energy out the cooling tower, get it out of the building, and now you have your thermal storage tanks devoid of energy, and they're all ice in the morning, ready to help the building cool in the next day. So let's take a look at some of the efficiencies. What I decided I would do is look at one of those energy storage tanks. Okay, so about 2 million BTUs in that tank. And so if you look at the energy associated with getting that from a gas boiler, and let's say it was 80% combustion efficiency, 5% for getting the gas to the building, site source, we're going to end up delivering a total of 2.4 million BTUs to the load. Okay, that's the overall plan, and I'll tell you in a second where we're getting the extra energy from. So to do that with the gas boiler, you'd need about 3.1 million BTUs. Do the calculation. And on the carbon side of things, using the numbers from Local Law 97, you're looking at about 370 pounds of carbon equivalent there. Well, now let's do it with the electric storage heat pump. Well, we're trying. The goal is to deliver 2.4 million BTUs to the building. And I spoke about a COP. Everybody on the call here knows what a COP is, but we normally speak more in terms of kW per ton. So when you're talking cooling COP, what you have to remember is when you go change it to heating COP, you add 1 to it. And that makes sense. Let's say you have, in the example here, we had a chiller that has a 0.79 kW per ton. That is equivalent to a cooling COP of 4.45. Well, because you are adding the electricity, you're putting 1 unit of electricity in, you're moving 4.45 with the heat pump process, and now you have to reject 5.45. So it's a very high heating COP with a centrifugal chiller making ice. And so if you're taking that 2 million BTUs out of the tank, and you add the BTUs that are coming from the electricity, that's where you're getting the 2.4 million BTUs. Now that, if you do the calculation, comes out to about 129 kilowatt hours. You do the calculation with the grid that we have now, and it's about 82 pounds of carbon. So even with a non-clean, crystal clean grid, there is a major carbon reduction by going to a storage source heat pump with a source temperature of 32 degrees, namely freezing water to ice. So now let's look at energy costs. And I didn't want to go into a deep dive on this. I don't have any simulation of any exact building or anything of that nature. But I just wanted to kind of throw out some numbers that would, make some general sense. Now, this was taken from, energy cost data from, a year and a half ago when I started putting it together, may be different now. But the point is, for 1 million BTUs being delivered to the load, okay, and I just try to get it on some easy unit, 1 million BTUs going to the load. It's about 12.5 therms of natural gas, and the cost of natural gas back then, it's $15. The fuel oil, you can look at the numbers there, $3 a gallon at the time, 9 gallons, 26. Steam's kind of expensive. Electric resistance, obviously, there's a lot more kilowatt hours if you're not using a heat pump, and so that is, very expensive. So we try to avoid that. But if you use a storage source heat pump, and I used a 25-cent kilowatt hour all-in number just to come up with a cost. the point is it's relatively close to the fossil fuel options. Is this a detailed analysis? No, but it's in the ballpark. I'm not saying it's better. I'm not saying it's worse. I'm saying it's in the ballpark and certainly worth good analysis. So let's take it another step further. A lot of systems now are being designed with DOAS systems, which just essentially on the cooling side, they separate the latent cooling from the sensible cooling in a building. So they have two different coils. One hits the air, fresh air that's coming into the building. You take all the latent or most of the latent out of that. And then the sensible coils are in the different zones, and we do the sensible cooling there. It turns out that 32 degrees is a just about perfect temperature for a phase change for storing energy when you are running a system in this fashion. So all I've done is I've broken the cooling coils into two here. We have the sensible cooling coils down here, which are being supplied a much warmer temperature liquid. So we'll call this the high temperature coil, a cooling coil. You want to supply it with a temperature that's not going to cause any condensation. So that certainly has to be looked at. But it's clearly a much higher temperature for the chillers to operate at and at very, very high efficiency. Oops. Then you also have the DOAS coil. That's where the latent energy is being taken out of. You can very easily supply that with the thermal storage tanks, giving you a 42 degree glycol temperature going to those coils. And so you have a nice cold coil here, cold being supplied by ice, by the ice melting. And so you've separated out the DOAS, the cold coil from the warm coil. Now, if the numbers, weren't balanced or the system wasn't balanced right, you could certainly have the chiller operating and some of the cooling connecting over to the tanks, but I won't go kind of into that mode. Summer, nice night making. Since we started on the cooling side of thing, it's the same as it was before. We're charging, or we're taking the energy out. I got to get rid of the charging the tanks. We're actually discharging the energy from the tanks. We're taking the energy out and rejecting it out on the cooling tower. Morning heating with the DOAS system, it's the same. You're putting heat wherever you need it in the heating coils, and you are making ice. On the simultaneous nature with the DOAS, as I said, you can be running the chiller. The ice the tanks can absorb energy from both directions, or it can be helping cool, depending on if it's overloaded. And then finally, winter cooling mode. The tanks can be used for doing the DOAS coil or the sensible coils inside. In the winter time, there's not as much cold coil needed. The air is drier in the winter time, but certainly it can be done in particular situations that you may need. And then finally, heating, pretty straightforward with the storage source heat pump. So then you come to, well, what if there's not enough energy in the building? So some of the legacy buildings, they've got big server farms in them. They've got, computers in them that are, a lot on the desks. They have less efficient lighting systems. So in the new buildings going in, well, what if there's not enough waste energy to collect the day before to store the water? Well, you've got options. There's lots of ways to melt ice to store it. You could do electric resistance if you want. You could have a air coil outside. You could use air source heat pumps. You could have solar collectors, low temperature solar collectors. All they're trying to do is melt ice. So there's a lot of ways that you can melt that water other than just reject heat from the core of the building. But let's look at air source heat pumps as an option. So right now in some of the designs going forward, there's you've got DOAS systems. So you've got the low temp coil, the high temp coil. You can heat by making the ice, but what if there's just not enough? Well, you're throwing on air source heat pumps. So air source heat pumps are going to be able to give you that 95 or the 100 or the 110 or whatever you need for those coils. And it's taking the energy out of the air outside. So now we're not bringing fossil fuels into the building. We're still using electricity, and it's an all-electric building, and we are going to be heating the building. And we're getting BTUs into the building by pumping it out of the cold air outside. Perfectly doable. You need to have a bunch of the air source heat pumps on the roof. These things, the reason they're very popular in the center of the country is because it's a more mild climate. When you get up to our area, you got 0 degrees or -2 or 3 or 4, and these things become relatively inefficient. I don't know the exact numbers, but somewhere in a COP in a 2 or 2.5 range. So relatively low. But on those super cold days, you're going to need to get your energy from somewhere, and the air is the source in this case. The other impact that you can have on these air source heat pumps is, what if it starts snowing? What you have this really cold coil that's trying to make the air even coil. You have to get into different things like melt and defrost cycles. So they are subject to the elements. Well, one of the things that storage allows you to do is spread this load over time. And so I threw on just a heat exchanger, and now the air source heat pump, if it has extra energy to give, maybe it could be a source for melting ice and storing that energy for a later usage. And it actually turns out to be very similar to what you do in air conditioning with what we'll call the ice storage tank. So remember when I spoke about partial storage system where you have a 1,000-ton chiller and storage, and the storage makes enough cooling at night. The chiller makes enough cooling at night to then run this smaller chiller, this half-size chiller, 1,000 tons, and the storage helps that 1,000-ton chiller meet the 2,000-ton design load. So you've actually designed the chiller plant. All it has to do is meet the average cooling load on design day, the 24-hour average. And most buildings don't have much cooling load at night, and that's why we can do that. Well, if you think about doing that with the air source heat pump, you can kind of do the same thing on the heating side of things. So the chart basically shows hold on 1 second. Let's talk to you more about heat pump. So the chart is showing two different things. It's got two different scales. The blue in the background goes to the scale on the right, and that's the amount of BTUs in this storage tank system. And so the total amount of energy storage is about 95,000 ton hours, because you're going to the scale on the right. On the left-hand scale, we're looking at the load profile of the building. So the red is meeting the absolute hourly load profile of the building. The orange is also the heating load profile of the building. And what we have here is a building that has a peak of about 12 million BTUs, but we put in a heat pump that has about 5.5 million BTUs of capacity. And during the day, when the heat pump's running, it is meeting the load, and it's melting some ice. So that's the blue bars. And you're putting energy into storage. So you can see the storage inventory growing. And then when you get to the on-peak hours, and this on-peak hour is going to be a big deal for the utilities as we move towards electrification. And it's peak hours now in the wintertime, but it's going to get much more intense as we add heat pumps. So in this particular case, we have turned off the air source heat pumps totally. So we've gone to full storage here. And now we're taking all the energy out of the storage tanks, or not all of it. We're taking energy from the storage tanks and pumping it up to a usable level and meeting the load of the building. Now, a better way to see the graphics on just how much energy you have stored in these tanks. Now I only have one scale. I've got, just the 100 million on the left. And so this is the same building load profile down here, but now I'm showing you how much energy is in storage. And even after the design period on design day, the 6 coldest hours of the day on design day, we still have about half our storage left over, which we could use again the next day, even if we didn't rebuild the way we did. So there's a lot of energy storage at the building, and the thing about it is the energy's in the building, and it's right next to surface area that is clean and undisturbed, right? So it doesn't matter what the outside temperatures are. It doesn't matter if it's snowing. It doesn't matter if coils are frosting up. You've already got this water in the tank ready to go and ready to be converted into energy at a usable level. So to summarize, the system will meet the electrification goals of the city. Large amounts of carbons can be saved by not wasting that energy through free cooling. You're saving it for tomorrow morning's warm up. There's large amounts of water that's not being evaporated off. So in green buildings, that's a lot of water that you're not wasting with free cooling because you're not running that cooling tower. We have energy storage system being used effectively the entire year. So that capital expense is used well. The capital expense for the air source heat pumps and chillers can be reduced because you've got a thermal storage system in there that can help you design for the average load instead of the peak. And you can have the exact same redundancies and safety factors as you do in any other design. Tell us what you need for that, we can give it to you. The electric peak load reductions are available for winter and summer. So in the summer, I don't have to go into that explanation, but let's look at that period that we had right here. So now, instead of having air source heat pumps running at a COP of about 2 or 2.5 to meet the peak load of this building, at this point, we are running a centrifugal chiller making ice at a heating COP of about 5.5. So in comparison, as far as peak load reduction, you have cut the demand that you would have had in the building with the air source heat pumps in half or by more than in half. Now, it's true, some of this energy might not be waste energy that you saved. And in this example on design day, we took that, but a heat pump running from, let's say, 0 up to an ice melt temperature of 45 is a very, very high COP heat pump. So your demand reduction is there, and it's dramatic, especially when the utility is going to be needing that demand reduction. And obviously, there's major energy cost savings by reducing the peak demand both in the summer and the winter, and saving the BTUs from the free cooling from the night before. So there's obviously things that you got to look at. You got to look at the coincident heating and cooling load profiles by season. You remember one thing that, in the wintertime, increasing fresh air, that used to help on the whole free cooling thing. You wouldn't want to do that now, okay? Because now that free cooling is wasting energy that you want to save for tomorrow. So you want to save that by melting ice. In the summer, you always want the tanks full of ice in the morning. And now in the morning, when the heating in the winter, in the morning, your goal is to have 100% water before you get into the heating. And so in the spring and fall, it's going to be somewhere in between those two extremes. But that's certainly something that needs to get looked at. But there's seems to be plenty of push in the amount of storage that you'll have in the winter if you size by the summer cooling load. And then 95 is doable with existing ice-making centrifugal chillers right now. If higher temperatures are needed, you'd have to look at either second stage heat recovery chiller or a screw recovery that can do a higher lift. But certainly very doable. So there's lots of energy storage in New York City now, in a lot of the legacy and some of the new buildings. And so there's a lot of energy, thermal energy and heat that's in these buildings that could be used with a storage source heat pump system. And so with that, I am happy to take any questions you may have. Thank you very much.
Thank you, Mark. Okay, everyone, if you could just please use the questions box for your questions, and I'll ask them for Mark. So our first question, somebody would like to know if a similar system can be developed using water source heat pumps instead of a chiller.
Sure. Water source heat pumps are reversible chillers. I mean, you can think of them either way you want. They have advantages that you could reverse it and throw the energy out throw the energy away with air, as opposed to throwing it away with a cooling tower. Because remember, that's what that cooling tower is doing. It's throwing energy away, and that's what the condenser air coil on a reversible heat pump is doing. It's throwing any energy away with that coil when you're cooling the building, and it's absorbing that energy when you're heating the building. So sure, yeah, no problem. Other questions?
Anybody else have any? Right now we only have that one. Does anybody else have any questions?
There's talk about PCMs, other phase change materials other than water, and I hope that I made the point clear that water is an amazing material that's free to us, and it does this incredible phase change at a temperature really close, almost ideal, and in fact I would say at an ideal temperature for space heating and cooling. And if you try to modify that temperature up a little bit, people think it's we could do a little bit warmer temperature. It cuts the amount of storage capacity in half. There is cost. Nothing's cheaper than free, and the cost of materials are pretty extreme. Our company's done a lot of research over the years in phase change material, and we landed on water for numerous reasons. And certainly for heating and cooling buildings, it's my strong belief that water is the way to go, because we could put other materials into this product, and other manufacturers, you can do it, but cost, space, amount of storage tanks you need, it doesn't make any sense.
Another couple just came in. They would like to know a simple explanation of how new requirements for outside air related specifically to COVID would be managed with this type of system.
Well, I'm not changing how what your fresh air requirements are in the building at all. You would handle it the exact same way. You would handle the air and the air purification. This is only a matter of the energy side of heating or cooling the air. It's not a matter of purifying the air.
Next question is it practical to use thermal storage in single-family housing? And what about an apartment building also?
So take the single family first. Single family is difficult. Well, if we're talking about a home, right, in suburbs, etc. It's difficult. Their load profile, if you look at it, is more like that of a hospital, we'll say. Okay, big load during the day, 50% load at night. So on Long Island, you have a house, 5-ton house. It's probably averaging two tons at night to stay cool on a summer evening. So it's not like a commercial building where you have not much going on at all in the space at night, and so you can dedicate the chillers to making storage. So in a home, you kind of have to have two systems. You have to have one to meet the night load, and then one to be making your storage and then using it for the house. So it makes it more difficult. There may be more passive ways to do it than the active system. In high-rise residential, if it's through-the-wall PTAC type units, then I would say no. It's difficult. If it's centrally cooled with a chiller, I would say absolutely, no question about it. And we're even looking into if, a lot of the buildings have heat pumps in the high-rise buildings, and they have a water loop. You could certainly condition that loop. So in the summertime, you normally in a building like that, you're using a cooling tower to cool that loop to, let's say, like 80. And all the heat pumps in the residential building are cooling, using that 80 degree to reject their energy into their heat into. Well, you could use a storage system and cool that loop down to 55 or something of that nature, and all those heat pumps in the buildings would get dramatically more efficient, and so they would get more capacity, more efficient, and it would reduce the peak load. So there are ways to apply energy storage to these other buildings. Somebody asked me in the last presentation I did on, well, why aren't you doing a ground loop? Well, I mean, there's not a lot of ground to connect to in dense urban environments like New York City. You certainly can do it, but it's challenging. But in the suburbs, you have ground loops that you could put in. You could use those ground loops for melting the ice. It would put less load on the ground loop. Usually ground loops are sized for peak load. Well, again, if you have this storage, you could reduce that peak load on the ground loop. Some people say that thermal storage in the ground is thermal storage. It is, absolutely it is. But you need massive amounts of surface area to connect to it. And sometimes it's kind of better to collect that energy and have it near the massive heat exchanger, namely the one inside these tanks.
Okay. Next question is, can you talk about the impact the thermal battery has on the quantity of chillers that would be required compared to a carbon neutral system without ice?
Well, I would say the impact, as I mentioned, usually when we are designing a building with storage that's focused on cooling, we are knocking the size of the installed plant down by a third. As a for instance, we did a building in New York City, new construction downtown. big headquarter building of a company. And the original design was for 6,600 tons of chillers. They went with 4,400 or 4,500 tons of chiller, and they put storage in. They saved 2 megawatts off the peak design, peak load of the building, and it had the same N+1 redundancy that was specified for the building. So in the cooling side of things, depends on type of building, application, etc. But you can usually knock a third off the chiller plant. I mean, normally when I explained this in one of my ASHRAE articles. I ended it with engineers think they have a 1,000-ton building, they add 20% for redundancy and cushion, and actually that's what the GSA says to do for in P100 on designing buildings. What I say to do is reduce by 20% the peak, the chiller plant, reduce it by 20%. So take it down to 80% of what the design was, and now add storage. And you can get the same redundancy and the same safety factor with that. Now you have an asset that you can use to take advantage of lower peak pricing or storing energy for renewables or anything else. The point I was making during the talk is that the same way you are doing that for air source, for cooling side, designing the chiller plant to the average 24-hour load on the chiller plant, you can do the same with those air source heat pumps. So, if you were putting in, couple million BTU air source heat pumps, you could put in 4, or maybe even 3. I don't know. I got to look at the designs. But the point is, you can reduce CapEx by designing the plants based on the average 24-hour design day load, because you have storage as that cushion.
We are at 6 o'clock, so if anybody would like to leave the webinar, that's fine. Please just make sure again to fill out the questionnaire if you need PDH credits. Anybody else that I didn't get to your question and you would like to ask Mark, just hang on and I can let you ask a question.
All right. Well, thank you, everybody. I appreciate your time.
Mark, I think there's still a couple people on, so I'm just going to give it a minute.
Oh, sure. That's fine. I mean, I can take more questions if people want to, doesn't matter to me.
Okay. If you are staying on to ask Mark questions, you should be unmuted currently, so you can speak.
Hi there, this is Amaury de la Cruz from Con Edison. Thanks for your presentation today. I had a question for you, just sort of following up a little bit on this idea. I wonder if you could speak to what are some of the challenges that you encounter when trying to help customers or engineering teams design these kinds of non-fossil fuel related heating systems, and what you have seen to be some of the things that have helped overcome those challenges and get these deployed, whether it's as a retrofit to an existing building or a new construction.
Mark, I think you're muted right now.
There we go. There we go. Okay, I was trying to unmute. Thanks for the question. Well, I mean, quite honestly, if we had Con Edison by our side on a project to try this out, I think that is a big boost. I think there are certainly some research development projects that could go in, some demonstration projects that could go in. You know, there's lots of energy storage for cooling buildings installed in New York now, and certainly they could be converted over for this, because most of them probably have a lot of free cooling.
Yeah, I'm interested. I manage energy efficiency programs, and we're looking at what they call the clean heat program, where we're trying to get help customers either defer or replace fossil fuel heating with electric heating, like heat pumps, or like the types of hybrid systems that you're talking about. So I was really interested in trying to understand what might be some of the challenges that you've seen that tend to stop people from deploying these systems, and if you've had any success stories that you could share, helping us sort of guide the way into how we can help folks take advantage of this approach.
Well, you know, I'm probably best that we would, you know, take the discussion offline, you know, because I don't want to get into commercial, you know, discussion on it. But there are certainly things that Con Ed could help with on getting projects to move forward. I have a few in mind right now that would be good to talk to you about. And say hi to Dave Pospisil for me.
Amari, if you would like, I can connect you with Mark after the webinar and send an email to both of you.
Everything.
You have each other's contact info.
That'd be great. Thank you.
You're very welcome. Make a note for myself so I don't forget.
Hi, this is Marcin Polak, Con Edison again. I have two questions. Maybe one of them is the space needed for the thermal storage, and the other one would be the cost per ton of the thermal storage. Thank you.
So space, I usually try to explain that to people in ratio, and I have a couple ASHRAE articles on our website that goes into the details on these things. But usually what we're trying to do in the design is take a third off the peak, you know, the peak cooling load, something like that. And when you are doing that amount of cooling, it turns out in most, you know, New York City type buildings, you need 1/4% of the space, now of the air conditioned space. Now the tanks don't have to be in the air conditioned space, but you use it as a rule of thumb. So for instance, a 1 million square foot building would need about 2,500 square feet for the storage in that case. And from, you know, the one example that I showed, that would give you a couple days worth of heat, you know, or not heat, but energy sitting in the tanks when they were fully melted, you know, ready to be turned into energy or into heat for the building. And so I think the third, 1/4% multiplied by the occupied space of the building is about what it turns out to be. We did a building in New York. It was 2.2 million square feet, and it was 5,700 square feet for the tank. So the ratio's, you know, just about right there. And I think that ratio would be as good or better on the heating side of things. As far as the costs, you know, we've got a lot in, there's certainly help you need when you're doing retrofit. Like you guys have had a demand response program, which helps on that cost because doing any work on a building in New York is expensive. In new construction, the cost is not, I mean, we have buildings that we've done in new construction. Just using that example, I did 4, if you have a 1,000-ton building, and GSA would say you put in 3 400-ton machines, giving you a total of 1,200 tons. Well, I would say put in 2 400-ton machines, and the money is saved on the third machine, the third cooling tower, the condenser pumps, the electrical going into the mechanical room. That money can pay for the storage. And we have projects where this has been the case. Now, it doesn't always work that way, but in new construction, it doesn't have to be, it's not this big cost add. It's just a different way to design the building. Now space is expensive in New York, but I mean, the basements that are getting cleared out because of having to take mechanical system up above on the second floor, our tanks can go down in that, completely waterproof. So, but we certainly, the demand, the peak load reduction incentive program that you had in place that was not in place this year, I'm certainly hoping it comes back next year, makes a big difference in getting projects moving forward.
Thank you.
Any other questions? Well, Natalie, it sounds like we're done.
I think so. Thank you guys for
Thanks, guys.
sticking around. Thank you, Mark,
You're welcome.
for the presentation. We appreciate it. And we'll see everybody next time. I'm going to close the webinar.
Okay, great. And they have to get their credits. So, okay,
Yeah,
thanks a lot.
It'll automatically pop up it should automatically pop up when I close it or when you guys.
Maybe people are waiting for that. Okay. All right. Bye-bye.
Okay. Thank you, everyone.